NASA's Artemis 2 mission, the first crewed flight around the moon in more than 50 years, has just been delayed. The reason is not a dramatic explosion or a visible hardware failure. It is something far less visible, but far more persistent. A hydrogen leak detected during a fueling test of the Space Launch System, or SLS. At first glance, this may sound like a routine technical issue. Rockets are complex machines, and test delays are not unusual. But this particular problem is familiar. Hydrogen leaks have followed NASA across decades of launch history. And now, as Artemis prepares to carry astronauts beyond low Earth orbit, the question becomes harder to ignore. Is this simply a fixable operational issue? Or does it reveal a deeper constraint within the SLS design itself? So let's take a closer look. If you value calm, step-by-step explanations that separate signal from noise, consider liking the video and subscribing. It helps this channel continue focusing on clarity over speculation. The delay centers on a fueling test conducted for the Artemis 2 mission at Kennedy Space Center in Florida. During this test, NASA was performing what is known as a wet dress rehearsal. This is a full practice countdown in which the rocket is loaded with cryogenic propellants, extremely cold liquid fuels, but the engines are not ignited. The issue appeared during the loading of liquid hydrogen into the core stage of the Space Launch System. Specifically, sensors detected elevated hydrogen levels inside a cavity located at the tail service mast umbilical. This is the ground-to-rocket interface that transfers propellant from the launch pad infrastructure into the vehicle. During the initial slow fill phase, operations were stable. The leak became noticeable only after the team transitioned to fast fill, when pressure and flow rate increased. Hydrogen concentration inside the monitored cavity rose toward predefined safety thresholds. NASA halted the operation as a precaution. Later in the countdown, during the final pressurization sequence at approximately T-6 minutes, hydrogen levels spiked again in a way that was not fully predictable. At that point, NASA called off the test. As a result, Artemis 2 has been moved to a later launch window while engineers investigate and address the issue. To understand why this hydrogen leak matters, we first need to understand how the fueling system of the Space Launch System actually works. 1. What is the tail service mast umbilical? When a rocket is sitting on the launch pad, it is not self-sufficient. It relies on extensive ground infrastructure for power, data, environmental control, and most importantly, propellant loading. The structure that physically connects the rocket to these ground systems is called an umbilical. On SLS, one of the most critical umbilicals is located at the base of the rocket and is known as the tail service mast umbilical. This structure delivers liquid hydrogen and liquid oxygen into the rocket's core stage. Liquid hydrogen is stored at extremely low temperatures, around -253 degrees Celsius. At that temperature, hydrogen becomes a liquid and can be stored in large insulated tanks. But keeping hydrogen in this state requires precision. Any warming can cause it to boil rapidly, increasing pressure inside the system. At the interface between the ground system and the rocket is a component known as a quick disconnect. This is a specialized coupling that allows propellant to flow during fueling, but must detach cleanly at liftoff. It cannot be permanently sealed because it needs to separate milliseconds before launch. That design constraint makes it inherently difficult to achieve a perfect seal. 2. What happened during slow fill and fast fill? Fueling is not done at full pressure immediately. NASA begins with a phase called slow fill. During this stage, hydrogen is introduced gradually. The purpose is to thermally condition the plumbing and the tanks. Extremely cold liquid hydrogen flowing into warmer metal causes contraction. If done too quickly, thermal shock could damage hardware. During slow fill in the Artemis 2 rehearsal, everything behaved normally. Hydrogen levels inside the monitored cavity remained within expected limits. The transition to fast fill is where the situation changed. In fast fill, the flow rate increases significantly. Pressure inside the lines rises. This is necessary to fully load the large hydrogen tank in the core stage. When pressure increases, the mechanical stress on seals and connection points also increases. If a seal has even a microscopic imperfection, hydrogen can escape. Hydrogen is the smallest molecule in existence. It can pass through gaps that would contain larger propellants like kerosene or methane. Under high pressure and cryogenic temperatures, maintaining a leak-free interface becomes extremely challenging. During fast fill, hydrogen levels in the cavity began rising into the low teen percentage range. NASA has defined flammability thresholds for hydrogen concentration. If hydrogen accumulates beyond certain levels in confined spaces, it can pose ignition risks. Although some leakage is expected and allowable, the readings approached predefined limits. The team halted the operation, allowing pressure to drop. As expected, hydrogen concentration decreased when flow stopped. At that stage, the behavior was concerning, but not catastrophic. 3. Why did the leak reappear during pressurization? After completing the fueling sequence, NASA reached what is known as replenish mode. In this state, the tanks are full, and small amounts of propellant are continuously added to compensate for boil-off. The next critical step during a launch countdown is core stage pressurization. This is when internal tank pressure is increased to prepare for engine ignition. The tanks must be pressurized to maintain structural rigidity and proper propellant flow to the engines. It was during this T-6 minute phase that hydrogen levels spiked again, but this time more rapidly and less predictably. Pressurization changes internal forces inside the tank and plumbing. Seals that may appear stable under one pressure regime can behave differently under another. Materials contract at cryogenic temperatures. They expand slightly when warmed. Microscopic alignment shifts can occur. The quick disconnect seal used on SLS is pressure assisted. This means that under certain conditions, increased pressure can actually help the seal tighten. NASA successfully used a warm and repressurize technique during Artemis 1 to improve sealing behavior. But in Artemis 2's test, the hydrogen behavior during final pressurization was unstable. Engineers could not immediately confirm whether the leak would remain within allowable limits under launch conditions. Because this occurred during a critical phase of countdown, just minutes before simulated liftoff, NASA chose to stop the test. From an operational perspective, this decision reflects risk management rather than failure. A wet dress rehearsal exists specifically to expose unknown behavior before astronauts are involved. 4. Why is hydrogen so difficult to work with? Hydrogen's performance advantages are well known. When paired with liquid oxygen, it produces one of the highest specific impulses of any chemical rocket propellant combination. Specific impulse is a measure of propulsion efficiency. It indicates how effectively a rocket converts propellant mass into thrust. Hydrogen engines provide more thrust per unit of fuel mass compared to kerosene. Hydrogen also has excellent thermal properties. It absorbs heat efficiently, making it useful for cooling engine components before combustion. However, these advantages come with trade-offs. Hydrogen is extremely light and has very low density. That means tanks must be very large to store sufficient mass. Larger tanks create more surface area and more connection points. Every connection point becomes a potential leakage pathway. Because hydrogen molecules are so small, they can migrate through microscopic gaps in metal interfaces. Under cryogenic conditions, metal contracts unevenly. Even tiny changes in alignment can create leakage paths that are invisible during inspection. Historically, hydrogen has caused repeated launch scrubs during the space shuttle era. Shuttle missions averaged close to one scrub per launch attempt. Hydrogen leaks were among the most common causes. The Space Launch System inherits substantial design heritage from the shuttle program. Its core stage uses engines derived from shuttle main engines. Its fueling infrastructure evolved from similar architecture. This means that while SLS is a new vehicle, it operates within the same fundamental physical constraints. 5. Why not simply eliminate hydrogen? If hydrogen is so difficult, why does NASA continue to use it? Switching propellant types is not a minor adjustment. The entire vehicle architecture is designed around hydrogen's properties. Tank sizes, engine combustion chambers, plumbing diameters, thermal insulation systems, all are optimized for this fuel. Changing to a denser fuel, like methane, would require redesigning the rocket from the ground up. That would involve new engines, new tank geometry, new structural analysis, and likely new ground infrastructure. NASA's stated goal is not to eliminate hydrogen leaks completely. Engineers recognize that small, controlled leakage can be acceptable if it remains stable and predictable within safety margins. The objective is consistency, not perfection. The key issue during Artemis II's rehearsal was not simply that hydrogen leaked. It was that its behavior during pressurization was not fully understood in real time. Understanding and stabilizing that behavior is now the central focus of the investigation. Up to this point, the hydrogen leak may sound like a contained engineering problem. But Artemis II is not just another launch. It is the first crewed mission of NASA's Artemis program and the first time astronauts will travel around the moon since the Apollo era. That context changes the weight of every technical decision. The Space Launch System was designed to serve as the backbone of deep space exploration. Unlike commercial launch vehicles that primarily operate in low Earth orbit, SLS was built specifically to send heavy payloads, including the Orion spacecraft, beyond Earth's gravitational boundary. It is a core pillar of the Artemis architecture. If SLS operates as planned, it enables a sequence of missions. Artemis II will fly astronauts around the moon. Artemis III aims to return humans to the lunar surface, and later missions are intended to support the construction of a sustained lunar presence. In that framework, reliability becomes cumulative. Each launch must build confidence for the next. However, hydrogen management remains one of the system's most delicate operational elements. If recurring leaks continue to require repeated troubleshooting at the pad, schedules could stretch. Extended delays can increase mission cost, introduce logistical strain, and complicate coordination with other program elements such as lunar landers and spacesuits. This is where the broader strategic question begins to emerge. The U.S. Congress recently advanced the NASA Reauthorization Act of 2026. While the bill largely reaffirms Artemis, it also increases scrutiny of how missions are executed. Several amendments explicitly encourage expanded commercial participation in deep space cargo and crew transport. The language is measured, but the signal is clear. Policymakers are open to alternatives if they demonstrate capability and reliability. Commercial heavy-lift vehicles are developing along a different path. SpaceX's Starship, for example, uses methane rather than hydrogen. Methane does not match hydrogen's peak efficiency, but it is denser, easier to store, and less prone to leakage at cryogenic temperatures. Starship is also designed to be fully reusable, potentially allowing higher launch cadence. Blue Origin's New Glenn follows a similar methane-based approach and is undergoing incremental upgrades to increase thrust and payload capacity. A proposed heavier configuration could approach SLS class performance. None of these vehicles have yet replaced SLS in NASA's deep space architecture. but their development introduces a structural comparison. If commercial systems demonstrate consistent reliability, lower operational complexity, and competitive payload capability, long-term procurement strategies could evolve. If SLS resolves its hydrogen challenges and demonstrates stable launch performance, it reinforces NASA's current path. If difficulties persist, the conversation about alternatives may become more concrete. This moment, therefore, is not only about a single leak. It sits at the intersection of engineering constraints, policy oversight, and the evolving balance between government-led and commercial space systems. At this stage, several key questions remain unresolved. Engineers have not yet publicly confirmed the exact root cause of the hydrogen spike observed during final pressurization. The investigation will focus on the quick disconnect interface inside the tail service mast umbilical. Teams are expected to inspect the seals for signs of misalignment, surface damage, or contamination. Even minor debris or slight deformation under cryogenic stress can influence leak behavior. Another variable is the rollout environment. Transporting the fully assembled rocket from the vehicle assembly building to the launch pad introduces vibration, mechanical stress, and environmental exposure. These factors are difficult to perfectly replicate in ground-based testing. If alignment shifted during rollout, that could explain why the leak behaved differently under pressurization compared to earlier validation tests. NASA has indicated that repairs may be performed directly at the launch pad, avoiding a rollback to the assembly building. That decision will depend on inspection findings. A pad-based repair would shorten schedule impact. A rollback would extend investigation time, but allow deeper access. Looking forward, the next critical milestone will be a repeat fueling test. Only by loading cryogenic hydrogen again under real pressure conditions can engineers confirm whether corrective actions have stabilized the system. There is no laboratory substitute for full-scale propellant flow at launch parameters. At the program level, Artemis II now awaits verification that fueling and pressurization remain stable throughout countdown conditions. If successful, confidence in SLS operations would strengthen ahead of crewed flight. If further anomalies appear, NASA would need to reassess not only hardware fixes, but operational margins and risk posture. For now, the story is still unfolding. The hardware is under review. The policy environment is evolving, and the next set of data will shape how Artemis moves forward. As new test results and decisions emerge, this situation will likely continue to develop. Following the progression closely may provide a clearer view of how America's return to the moon ultimately takes shape.